Good evening. Today I'm going to deal with the second part of the second chapter. I have already uploaded the first part of the second chapter. I hope you've gone through it. Now, if you've gone through that first part, you might have come across four very important terms which I want to go through once more so that you are very sure about what these terms mean. The four terms that I'm talking about are, first one is potential. Second one, potential, which we denoted by the letter V, whose SI unit was joule per coulomb. And the second term I'm talking about is the potential energy, denoted by the letter U, whose SI unit is joules. Then there's potential difference and potential energy difference. So these are the four terms I'm going to discuss before I go into the next topic of this chapter. Now, if you have a, let's say, positive source charge Q, and I'm going to consider 2 points P and R close to the source charge. Because this source charge is positive, you know the electric field is going to be away, radially away from the positive source charge, because electric field is force experienced by unit positive charge. So when you keep a unit positive charge, it's going to be repelled, and so the electric field is always away from a positive source charge. Now, last session we discussed that E equal to minus dB by dx, and because electric field is a vector and this potential is a scalar, the negative sign indicates that the direction of electric field will be in the direction of decrease in potential. So because electric field is in this direction, you know that the potential is decreasing in that same direction. So here the potential, which I denote by V, P, V at P must be greater than V at R. So this must be larger and this must be a lesser potential, because as you move in the direction of electric field, the potential is decreasing. So now if I write work done, that is work done by the external force, that is there is an electric field that is pushing the positive 1 coulomb, the unit charge, away. But if an external force is going to displace it, bring it closer, it is going to bring it closer, dx, you have an external force, F external, you are applying in this direction, so that your 1 plus 1 coulomb moves from R to P. You have to do work against this field. So this work external to move the charge 1 coulomb from R to P is going to be equal to the difference in potential between the two, because potential difference, now I'm talking about potential difference. Potential difference is the work done to move unit charge from R to P. So that will be the potential difference between these 2 points. This is going to be equal to final potential Vp, because final destination is here, minus the initial point, that is R. So this work done to move a unit positive charge from R to P, that work done by the external force, that is what you call as potential difference between the 2 points. Now suppose this point, this first initial point was at infinity. Then if this point R is at infinity, you should know that VR is equal to 0, simply because yesterday we did the formula V equal to 1 by 4 pi epsilon 0 Q by R. So where R is the distance from the source charge. So if your R is at infinity, you know V is inversely proportional to R. So what will happen is V equal to KQ by R. This V will become 0 when R is equal to infinity. So if you take this point R to infinity, it means that the potential at infinity is 0, because when the distance becomes infinity, potential reduces to 0. So I am writing VR equal to 0. So then the work done by the external force to bring that charge 1 coulomb from infinity and place it at P will be Vp minus 0, and that is what you call as the potential. So I hope these two terms are very clear to you. Simply potential at a point P means how much work do you have to do to carry unit positive charge from infinity and place it at point P against the field? That is what you call as potential. Potential difference means the difference in potential between these 2 points. See, this Vp, the potential at P is higher, the potential at R is smaller, lower. So there is a difference in potential. They are not equipotential. That difference in potential is what you call as potential difference. It is actually the work you have to do to move +1 coulomb from R to P. So the work done by the external force to move it from R to P against the electric field will be final potential minus initial potential, which will be positive because Vp is greater than Vr. So that is those two terms. Potential simply to bring unit positive charge from infinity and place it at a point which is at a distance r from the source charge. Potential difference in an electric field is how much work do you have to do to move a +1 coulomb within the electric field from one point to another point, and that is a potential difference between the 2 points. Now, if you are changing these words to potential energy, the only difference is you are not moving 1 coulomb, instead you are moving q coulomb, any charge. So, if you are moving q charge, then that terms change to potential energy and potential energy difference. So, if you are bringing plus q charge from infinity and placing it at point P, then that work done is what you call as potential energy. And if you're moving plus q charge from R to P, then that work done to bring plus q charge is what you call as potential energy difference between the 2 points in the electric field. We also learned the formula potential energy U denoted by U is equal to Q times V, because V stands for potential, which is for unit charge, multiplied by how much charge you're bringing, Q times V, and you get the total potential energy. So this is potential, this is potential energy, this is potential in joule per coulomb, and this is potential energy in joules. I hope this is very clear to you. And also, if a potential energy, see, work done to bring Q charge, the work external to bring Q charge from R to P and place it there will be equal to final potential energy UP, because this is the final destination, minus final initial potential energy UR. So I hope these 4 terms are clear to you: potential, potential difference, potential energy, and potential energy difference between 2 points in an electric field. If this much is clear to you, we can move on to the next topic. That next topic is on page 15. The topic is potential energy of a system of charges. Potential energy, like I told you now, energy, if you hear the word energy, you should know you're bringing Q charge from infinity and placing it. If you're bringing many charges, you're going to bring all of them from infinity and place it as a system. So now it comes under 2 subdivisions. The first one I have noted as in the absence of external electric field. Absence of external electric field. Now, if there is no external field, you mean, see, suppose there is a source charge, there is an electric field, and to bring a Q charge from infinity and place it somewhere here, you have to do work, because there is an electric field and you have to do work against the electric field. Now, what they are telling you is, in the absence of external field, that means there is no source charge, there is no external field. In such a case, you can bring any charge you want and bring and keep it here without doing any work, because there is no field against which you have to do work. Therefore, I'm going to simply bring Q1 to A and place it, and that means the work done to bring Q1 to A is 0, because there is no external field. Now, keeping Q1 here, if I'm going to bring another charge Q2 from infinity and place it at a distance R12, R12 is this distance. If I'm going to place it here, now I have to do work, because this Q1 will now act as a source charge, producing a potential here. So I'm going to mark the potential of Q1 here as V1. V1 means because you have a source charge, this source charge will produce a potential here, and that potential is what I call as V1. And the formula for V1 I taught you yesterday, 1 by 4 pi epsilon 0. Source charge here, this is because of Q1, and the distance is R12. Potential at a distance R12. So now to bring this charge Q2 from infinity and place it here, I have to do work, which is given by QV. I am bringing charge Q2, so Q2 into the potential at that point is V1. So I will substitute for V1 and I have this formula 1 by 4 pi epsilon 0 Q1 Q2 by R12. Now that both are here, if I want to bring a third charge and place it, let's say at C, at point C, I am going to bring a third charge. It's going to be kept at a distance R13 from these two, 1 and 3. And this is going to be a distance R23, that is distance between 2 and 3. Now to bring this here, I will have to now do work against the repulsion due to this and this, because these two are already there. Both of them will behave as source charges. So this Q1 will produce a potential here because this can now act as a source charge. So Q1 at a distance R13 will provide a potential V1, and Q2 also will provide a potential which I will call as V2, because now Q2 also can, they both are there, they both will have an electric field, they both will act as source charges and there will be potential there. So now to bring to C, WC, I have to do work due to this potential. I have to do work, which is I am bringing Q3. So that will be Q3 V1 plus I am bringing Q3 against Q2. Q2 is repelling Q3 too. So this is going to be the formula. So now I will write it on top. So that work done, WC, that is work done to bring Q3 to C, will be Q3 times V, V1 being the potential due to the source charge Q1, plus Q3 into V, which is V2, which is the potential provided by the source charge Q2. So this, if I substitute, it will be 1 by 4 pi epsilon 0 Q1 Q3 by distance between the two R13 plus 1 by 4 pi epsilon 0 Q2 Q3 by R23 because of these two. So now the total work done to bring all these three together and place it in such a manner is this plus this plus this. So how many terms do you have? 0 plus 1 by 4 pi epsilon 0 Q1 Q2 by R12 plus 1 by 4 pi epsilon 0 Q1 Q3 by R13 plus 1 by 4 pi epsilon 0 Q2 Q3 by R23. So this will be the total work done in bringing all these charges and keeping them together. Work done is the same as potential energy. So you may say WA plus WB plus WC is either, you may say it is a total work done to bring these charges together and keep it in this manner, or you may say call it as a potential energy of the system of charges. So you can bring 2 charges, you can bring 3, you can bring 4, you can bring any number of charges. Only remember, if suppose I were to bring a 4th charge, then I'll have to do work against this Q3's repulsion, against Q1's repulsion and against Q2's repulsion, because all of them will now behave as source charges. So I will write Q3 into V3, Q3 plus Q3 into V1 plus Q3 into V2. Each of them providing a potential there. So it will go on getting added up. Now I hope this is clear to you. Now next topic under this is, here we started off with no external field. So initially we didn't have to do any work. After that, what now we are going to do is, there is already an external field, and into that external field we are going to bring these charges. To make things simpler, in your NCERT textbook, for the next topic they are only dealing with 2 charges. You can bring 3, you can bring 4 in an external field, no problem. But in your NCERT textbook, when you're doing in the presence of an external field, we are only bringing 2 charges, and I am also going to do the same thing. So here we have, in the presence, suppose there is already an external field. There is some source charge and it is producing, already there is an external field here, and you have to do work against the field to bring the first charge itself. Now to make things simpler, we will take only 2 charges. One, I told you that. Second, we will consider this whole surface to be equipotential. That means every point on the surface is having the same potential. That's just to make our derivation simpler. So now, if I want to bring to A, I want to bring Q1 charge from infinity and keep it here. But there's already an external field which is providing a potential V here, equipotential surface, so every point has a potential V. So now work done to bring Q1 to A is not 0. I have to do work which is given by Q1V. That is, this charge I am bringing it and keeping it at a point where the potential is V. Now keeping this Q1 here, I am going to bring the next charge Q2 from infinity and place it here. Here also, since we are taking an equipotential surface, we have the same potential V, and this I need to place at R12, distance between 1 and 2. Now I'll have to do work against the field, which I will write as work done to bring Q2 to B is Q2V. This is because there's already a field, I have to do that work, plus this Q1 is now going to act as a source charge and provide a potential here. That will be 1 by 4 pi epsilon 0, 2 charges Q1, Q2 by distance between them is R12. So this is against the field, this is also against the field. So when I bring Q1 to A, you have to do work only against the field because Q2 wasn't there. When I bring Q2, I have to do 2 work. One, I have to do work against the already existing external field, which is Q2V. Then I have to do work against this Q1's potential here. Q1 will act as a source charge, providing a potential here, and that is how we get that 1 by 4 pi epsilon 0 Q1 Q2 by R12. Now if you bring a third charge, you will have to, if you bring Q3 here, you will have to do work against the field already. So Q3V is there, then plus 1 by 4 pi epsilon 0 Q1 Q3 by R13 plus 1 by 4 pi epsilon 0 Q2 Q3 by R23. So it goes on like that. So the only difference is, if there is no external field, you don't have to do work against any field. You just have to bring the first charge without doing any work. Bring the second charge, you'll have to do work against the repulsion due to the first one and so on. If there is an external field, these terms will be there extra because you have to do work against the external field. So I hope that topic is also clear to you. Then topic 6 on page 16 is potential due to an electric dipole. See, potential, as you know, is the work done to bring a unit charge from infinity and place it anywhere in an electric field. This electric field could be due to any configuration of charges. It could be because of a single source charge, which we did in the beginning. One single source charge. There is an electric field around the source charge, and if you want to bring and keep a plus 1 coulomb here, we found out V is equal to 1 by 4 pi epsilon 0 Q by R, where R is this distance. So this we already did as a first derivation. So you can have any charge configuration, and all charge configurations which have an electric field around them, you will have to do work to bring another charge into that field. So right now, the next one what we are dealing with is a dipole, potential due to a dipole. Now here I have drawn the dipole like this. I have drawn the dipole like this, where this is minus Q and this is plus Q. Now you know that and if this is the center, this distance is A, this distance is also A. Total distance is 2A, and the dipole moment given by the letter P is always directed from negative Q to positive Q. You already learned in the first chapter that this dipole has an electric field around it, and we derived expressions for E axial and E equatorial. E axial would be along the axis any point here, and E equatorial will be a line perpendicular to the axis passing through the midpoint. So we've already derived electric field expressions. What we're now going to do is derive an expression for the potential due to a dipole, not electric field, potential due to a dipole. So we are going to select an arbitrary point. In the case of derivation, when we are deriving potential, we are not going to take axial or equatorial line points. We are just going to take any point P around the dipole, and after the derivation is done, we will find the special cases for the potential along the equatorial axis and the potential along the axial line. So I am just going to select any arbitrary point P here, which is at a distance r1 from the plus q charge, and it is at a distance r2 from the minus q charge. From the center, I am going to mark the distance of point P as r. Now let this angle be theta. Theta is the angle between the dipole moment P and the vector r. All these distances are vectors. So dipole moment and the vector r, which joins the center of the dipole to the point P, makes an angle theta. Now here we need to find the potential at P due to the dipole. Potential, as you know, is a scalar quantity, and therefore we will simply be doing algebraic addition in this chapter, unlike the previous one. In the previous one, electric field, electric force are all vector quantities. So we had to do vector addition. But here we simply do algebraic addition. Because we are doing algebraic addition, we need to include the sign in the formula and when we do sums. Because how do you do algebraic addition? If both are positive, you add and put the positive sign. If both are negative, you add and put the negative sign. If both are unlike, you subtract, put the sign of the bigger one. So you need the sign in your formulas. So here, if I am going to take V1 as the potential at P because of source charge plus Q, then my formula would be 1 by 4 pi epsilon 0 Q by R1, because the source charge is plus Q and the distance to that point P is R1. V2 I am going to take as the potential at P due to the minus Q. So then the formula will be 1 by 4 pi epsilon 0 minus Q by R2. This is what I said. In this chapter, because we are dealing with scalars, I am including the negative sign of the charge because we need to do algebraic addition. So the total potential at P will be V1 plus V2. So I can take the common outside Q by 4 pi epsilon 0, and in bracket I have 1 by R1 minus 1 by R2. So this is your total potential at P because of the dipole. Now this R1 and R2 are distances of plus Q to P and minus Q to P. We want our final formula in terms of R, just like our electric field. Electric field, our formula was in terms of X, which was the distance of the point P from the center of the dipole. So here also we need to bring this to a better form where our final formula is in terms of R, that is distance of P from the center of the dipole, not in terms of R1 and R2. So now what we are going to do is change this R1 and R2 into terms of R. For that, I am going to draw a perpendicular here so that this is 90 degree. Now, if you look at, this is the 90 degree. So this happens to be the hypotenuse, and this vector A, I hope you remember that 2A is a vector. So this A is a vector. I can resolve this vector into two components. theta is here. So this will be the opposite component. So that will be a sine theta. And this theta, this is to theta, this is the adjacent side. So this is going to be a cos theta. I'll repeat once more. In the previous chapter, I told you P is a vector. P equal to Q into 2A. 2A is a vector which is directed from minus Q to plus Q. So A is now the vector that is opposite to the right angle. So this is a hypotenuse. I have taught you resolving last year. So this hypotenuse I can resolve into two components. If this is theta, the opposite side will be the sine component and the adjacent side to theta will be the cos component. Now, in this triangle, if you take this triangle here, this triangle, it's a right angle triangle, I can apply Pythagoras. So when I apply Pythagoras theorem, I'm going to write r1 square equal to, this is a hypotenuse because this is a right angle, square of this plus square of this. So that is a square sine square theta plus, I need only this distance, not the whole thing. This whole thing is r, but this much will be r minus the a cos theta. So I will write r minus a cos theta the whole square. If I open the bracket, r1 square is equal to a square sine square theta plus r square plus a square cos square theta minus 2ar cos theta. If I combine this and this, sine square theta plus cos square theta is 1. So I may write r1 square is equal to a square plus this a square sine square theta plus a square cos square theta is a square. Then I have a r square minus 2ar cos theta. Now this will be r1 square is equal to, I am going to take the r square outside. So this will be r square bracket. This will be a square by r square. So that when I open the bracket, this r square and r square will get cancelled and I have an a square here. Plus this r square has come out. So 1 minus. So I have taken r square outside. So this will be 2a cos theta by r. So that if I open the bracket, r square into this term, this r and this r will get cancelled and I will have the 2ar cos theta. What I want is 1 by r1 to substitute in v1. So that I am now going to take the square root. r1 is equal to, wait, before that, this a square by r square is an extremely negligible value because this is a short dipole, a is very small compared to r. r is a distant point. So compared to r, a is negligibly small. So if you take the fraction a square by r square, this is already very small. So square of that will be even smaller. Divided with the large term, this term a square by r square can be neglected. So I may write r1 square is equal to r square bracket 1 minus 2a cos theta by r after neglecting this term. Now I want 1 by r1. So I am going to take the square root first. When I take the square root here, this will be r1 equal to r bracket 1 minus 2a cos theta by r the whole raised to half. I have to take square root for this one, that is r1. Square root of this is r. Square root of this is what I have raised to half. In our formula, we need to substitute for 1 by r1, not r1. So I am going to take the reciprocal. 1 by r1 equal to 1 by r bracket 1 minus 2a cos theta by r the whole raised to minus 1 by 2 because reciprocal. So it is minus 1 by 2. Now I am going to apply binomial theorem. Those of you who haven't taken math, it's okay. Even if you do not know the binomial theorem, it doesn't matter, because in physics we only take the first two terms. So that I'll tell you now. So binomial theorem, 1 minus x raised to minus n, you need to just write 1 plus n times x. There are higher powers of x square, x cube and so on, factorial. There are a lot of other terms. But in our case, this x, that is 2a cos theta by r is x here. 1 minus x nu parayumbo, this term is that x term. This term is extremely small because a is small compared to r. So a small compared to r, this term is a very small term. So if you are going to take the next term, it is the higher power of x, x square. Then you have x cube and so on. But square terms will be even smaller. So all the rest of the terms we may neglect. So we need only the first two terms, 1 plus nx. So those of you who do not know the binomial theorem, simply by heart this and keep. I'm going to apply this here. 1 by r1 equal to 1 by r bracket. It is both negatives. So here also both negatives. So 1 plus nx. So n is half into this. So half into this, that 2 and this 2 will get cancelled. And you have a cos theta by r. So this is our final equation for 1 by r1. Now we have a 1 by r2 also in the formula for v at p. Now you don't have to go and derive that all over again. So you simply need to write similarly 1 by r2 equal to 1 by r. Please remember to change the sign, 1 minus a cos theta by r. So we have got the expressions for 1 by r1 and 1 by r2. This derivation is not required for you. You simply look at this, change the sign and write 1 by r2. I am going to substitute these 1 by r1 and 1 by r2 into our first formula for v. The formula for v that we had got was total potential at P. We got as V1 plus V2 if you remember. And we took Q by 4 pi epsilon 0 outside. And we had 1 by R1 minus 1 by R2. This was our formula. I am going to substitute for 1 by R1 and 1 by R2. So this is Q by 4 pi epsilon 0. This common for both 1 by R1 and 1 by R2 has a common R in the denominator, which I will take outside. So that inside the bracket, we only have 1 plus a cos theta by R minus 1 by R2. So both these terms will be given a negative. So this will be minus 1 plus a cos theta by R. And close the brackets. So now we have potential formula is given like this. This plus 1 and this minus 1 will get cancelled. Total potential at this point P because of the dipole will be Q by 4 pi epsilon 0 R. And in the bracket we have a cos theta by r plus a cos theta by r, which is 2a cos theta by r. Now if I combine these two, 2a into q, I hope you remember is dipole moment from last chapter. So I will replace this and write v equal to 1 by 4 pi epsilon 0. 2a into q I will replace with p. So this is p into cos theta by r into r. We have an r square here. So this is your final formula for potential at P. This 1 by 4 pi epsilon 0 you already know is 9 into 10 raised to 9. P is the dipole moment, vector quantity directed from minus q to plus q, and its formula is q into 2a. Theta is the angle between the dipole moment and the vector r, this theta. Okay. Now this is your final formula for the potential at point P from the dipole. I told you we will be taking special case. The two special cases that we are going to take are, we need to find out the potential along the axial and the equatorial axis. Now axis potential, suppose this point P is here. Let's say your point P is here. If your point P is here, it means that it is an axial point. It is along the, this is the axis of the dipole. this point P is along the axis. Your point P could be down here also. So if you are taking an axial point, it means your R will now be along the axis like this, which means R and P will be in the same direction. So this theta will reduce to 0. So for B axial, we know theta equal to 0. If I put 0 here, cos 0 is 1. And so we have B axial equal to 1 by 4 pi epsilon 0 P by R square. And in the case of equatorial axis, equatorial means your point P is along this line, that is a line passing through the center of the dipole. If your dipole is like this, a line passing through the center and perpendicular to the axis is what you call as equatorial axis. So your line is going to go like this. Your R is going to be perpendicular to the axis, so that your P and your R here will be perpendicular to each other. That means theta is going to be 90 and cos 90 is 0. So B equatorial is going to be 0. This is a very important result that you must remember for application questions, because if you have a dipole, the potential along the if your axis is like this, let's say your dipole is like this, and this will be your equatorial axis. Let's say this is your equatorial axis, okay? So if your dipole, this is equatorial axis, all along the equatorial axis there is no potential, zero potential. That means you can move a charge anywhere along the equatorial axis without doing work, because potential is 0. So if your dipole is along the x-axis, you can move a charge along the y-axis and the z-axis without doing any work, because potential along the equatorial axis for a dipole is 0. B axial is 1 by 4 pi epsilon 0 P by R squared. So we'll end the session here. Please go through this. I will record the next one and send it to you tomorrow. Thank you.